Welcome. In this video I'll discuss the advantages and disadvantages of staggered schemes, and these are a slightly variation or slightly different from the co-located or cell-centered schemes that we looked at so far. It has some advantages and also some disadvantages, and I'll try and explain what these are. One of the main advantages of using staggered schemes is their dispersion relations, and they avoid some of the problems that cell-centered schemes have with things like zigzag oscillations, which are also known as sort of red-black methods. So first I'll discuss cell-centered, also known as co-located schemes. So is it co-located? So because all quantities are on the same grid. So we have a bunch of grid points. So I'll draw this picture again. We have a bunch of cells. We have cell centers, which are here, and we have cell edges, which are these lines. And this is where we're calculating fluxes. So fluxes are calculated through here. If you think about the density equation, for example, you have mass density rho, and you have velocity u, which might be vectors, might have velocities in different directions. And then we want to calculate fluxes here. So we know rho and u on these cell centers, but we need to do some kind of basically either interpolation or some kind of reconstruction of the density and velocity to calculate these fluxes. And so the cell center method, some of the advantages are that because everything's in one location, nonlinear terms are quite easy. So if you want to multiply rho times u, they're all at cell locations, so it doesn't have any problems. But it has this problem that if we want to calculate fluxes at cell centers, fluxes at cell edges, we need to do this interpolation. So I'll change it to a red since it's a disadvantage here. So we have to do this mapping from the cell centers to the cell edges. And one of the problems that we'll analyze in a bit more detail later is that if you have these cell-centered schemes, there are usually zigzag modes which can occur. And one way to kind of visualize this is if we have let's say I'll draw this direction as like x, and then we have a density, for example, this is mass density rho. If we have a mode which looks like this, so we have density which is like going up and down like this, and now we're calculating the gradient. So at this point we calculate the gradient d rho by dx, for example. At this point, calculating d rho by dx typically uses these two grid cells. So we'd use those two, and we find that the gradient is basically 0. And the same calculating the gradient here would use these two grid cells, and so here again we'd find that has 0 gradient. And so this zigzag mode has the same derivatives as a flat, like constant density. And so this mode, there's nothing stopping this mode from growing or shrinking. And so typically you find that this mode can become unstable, and you end up with these kind of zigzags forming in the solution. So these are some of the problems that these cell-centered methods have. And so there are alternatives. So there's staggered schemes, which have some advantages and also some disadvantages we'll find. So we have the same picture here. We have, say, the cell centers, and here we might put the density, for example, at cell center, and you might evolve the velocity, for example, at cell edges. And this typically makes calculating fluxes much easier, because now we know exactly what the velocity should be at this location here. And so when you calculate fluxes, these fluxes become easier to calculate. Particularly if, for example, if you evolve the momentum rho u, for example. So I'll make this easier. So evolve rho u. If we want to evolve, say, the density equation, this is the flux that we need through the boundaries, and so evolving the fluxes becomes much easier. One of the problems is if we say, for example, we now want to calculate what is u, so ui. So you want to divide rho u by rho. So this is rho u divided by rho, but the rho u and rho are at different locations, and so this needs some way of, again, interpolating or mapping, reconstructing rho onto the same locations. And so I call this nonlinear terms, so terms which combine multiple quantities, and these are on different locations. A related problem is that if you now want to conserve mass, for example, so here we've got the mass density, so this is fine, this is being conserved in these volumes. But what if we also want to conserve momentum? Well, we need to define a different set of volumes for the momentum, and so we need to define essentially a different mesh. I'll try and draw this in here, so that the momentum is defined on these kind of staggered grids. So you now have two sets of grids. One is the black, is where momentum is being evolved, and one in red is where so one in red is where momentum is being evolved, and one in black is where the density is being evolved. And so you end up with two sets of grids. And so this becomes quite complicated if you have very complicated geometry, and it's just much more bookkeeping to try and keep track of two different sets of grids, and then the conservation of different quantities on different sets of grids, and the mapping between them. But it does, as I say, have some advantages, and it's easy to calculate fluxes. It is also typically has better dispersion relation properties, because if we try and look at this zigzag mode again, so if I have rho, this is x, so we have some kind of a zigzag mode like this. So alternating grid cells, positive and negative. Now if we calculate the gradients, so u is calculated at these points here, and so now there is a gradient at these locations. So u has a non-zero gradient. So d rho by dx is not equal to 0. Whereas in the cell-centered case, we were calculating the gradients at the same locations as the density, and so this kind of zigzag had 0 gradients. So here it's roughly 0. Whereas in the staggered case, the same zigzag has non-zero gradients, because we're calculating the gradients at different locations than the density. And we can show this a bit more mathematically by calculating the dispersion relation. And I'm going to just do in one dimension, so this is in x. I'm going to calculate, label j as the cell number, so this is j plus 1, so this is j minus 1, and I have a constant distance here, which is delta x between grid cells. And I'm going to solve an equation which is just a simplified sound wave again. So this is du by dt, is just depending on the pressure gradients, and the pressure is just the compression. So dp by dt is minus du by dx. So it's a very simplified form of, but it still has a wave. So this should have a wave with velocity. Velocity is just 1. So we should find that basically omega is equal to k, which should be the equation or the dispersion relation. And of course, when you solve this numerically, we'll find a different dispersion relation, but we'll see. So we're just going to try central differencing. So first, we'll do centered. That's just central differencing. And so we'll just write that dp by dx at grid cell j is roughly p at j plus 1 minus p at j minus 1 over 2 delta x. And the trick with these, so let's do dx here. The trick with these is to write p, which is some function of x and time. This is some kind of p naught, for example, times an exponent, which has a wave character. So this is the I, so it's kx minus omega t. So putting a wave into our system, and these x has only discrete values, so it's on each grid cell. So we have xj, for example. Here's xj, where xj is the location of each cell. So this position here is xj. And then what we have is that p at xj plus 1 and time is of course just the same thing, except now we have j plus 1, which is just xj plus delta x. And so this you can just write as p naught is the same thing, so k xj minus omega t. And then here we've added 1 to this, so this turns up as a factor e to the ik delta x, because that changes this from xj to xj plus 1. And the same with j minus 1 becomes e to the minus ik delta x. And so therefore we can write down this formula here. So we have dp by dx at location j, and that's this quantity here, so it's p naught e to the ik xj minus omega t, and then here we have these factors, so we can just write this is e to the ik delta x minus e to the minus ik delta x, all divided by 2 delta x. And here we can start to use some relationships to turn these into sines and cosines. So we have the e to the I theta is just cos theta plus I sine theta. And so this obviously cancels out the cos terms, and so this turns into a 2 times I times sine theta. And so this whole thing here, this will turn into a 2i, we have a sine k delta x divided by 2 delta x. And so now when you write down equations, I'll substitute in here. So we're going to write u as, again, u naught times the same factor, and of course then these factors will mostly cancel out, and so then here it has basically the same equation. So what we end up with is the d by dt becomes a minus I omega, so minus I omega u naught. This is the du by dt. There's just p naught, and then we're cancelling out these terms because that's common to both left and right side, times this factor here. So then we have a 2i, so k delta x over 2 delta x. So then there's a minus sign here as well in this equation here, so a minus here and a minus there. And of course the same thing for the other equations, so minus I omega p naught is minus u naught. I'm just going to cancel the 2's this time, so this is I sine delta x. Okay, so then we can substitute one of these equations into the other, and so we just say substitute this p naught into here, for example, and we end up with So we have a dispersion relation for omega squared, which is just the sine squared and delta x squared. This is the dispersion relation. Now the k has a range of values, so k can go from 0 up to a maximum. So the maximum k is just 2 pi over the minimum wavelength. So the minimum wavelength is the zigzag mode. So if you have a zigzag like this, so it consists of two grid cells like this, and the wavelength is 2 times delta x. This is the lambda minimum, and so k max is 2 pi divided by 2 delta x, which is just pi over delta x. And so if you put this into here, the maximum is when you have sine squared of pi. And so the plot what this looks like. So this is k, this is omega. The analytic solution, I said, was just omega is equal to k. Which is clearly not what this equation is. If the k max is over here, and this is when sine has an argument of pi, which is obviously 0, and so what this looks like is that small k follows the analytic form, and then it rolls over, comes back down to 0, and so omega is equal to 0 on this zigzag mode. So for the wavelength is 2 times the grid spacing, there's a 0 in the a 0 frequency mode. And in fact this gets a bit more strange, because if you now work out the group velocity, for example, there's a peak in the frequency, which is obviously half the maximum, and so in this region we have d omega by dk is less than 0, and so what you end up with is at high k, so on small scales, the direction of the wave actually reverses direction, and in some cases what can happen is if you have an advection equation where everything should move, say, left to right, you find waves which are moving in the opposite direction, so moving right to left. They're sometimes called parasitic waves. And they're waves which are purely due to the numerical method and move in the opposite direction to the direction they should do. So this omega versus k should just be positive, have a constant group velocity, but here the group velocity is positive and then switches sign to be negative. And these are unphysical waves due to the numerical scheme. And so typically if you use cell-centered methods you have this problem, and so you have to apply some kind of dissipation to damp these waves over here because they're unphysical. And so the staggered grids so has a similar, essentially the same relationship or the same derivation, except now what we do is we have when you're taking derivatives, actually I'll just draw it again. So here we have the x direction here. So now we have say these p's on here. So p at j plus 1. Now I have u, so at the half grid cells to j plus a half, and I have u at j minus a half. So for the pressure equation p, so we have dp by dx is minus, so dp by dt is minus du by dx. And now we write down that du by dx at point j, for example, is So now we work out du by dx at this location here in the center, which is this is this location here. And we're using these two values here to calculate this value here. And so write down that this is just minus the gradient, which is u at j plus a half minus u at j minus a half. So just take the derivative of these to either side. Now, because each one is only half a grid cell across, this whole thing is just delta x. This whole thing is just delta x here, over delta x. And so when we use the same analysis as before, what we end up with is an I minus I omega. This gives us P naught as before. And now we have a minus U naught, and then these things as before give us phases. So we have an e to the I k. Now it's a delta x over 2 minus e to the minus I k delta x over 2. So instead of being plus 1 and minus 1, it's now plus a half and minus a half. The whole thing just divided by delta x. And so as before, these just give minus u naught, and this becomes a 2 times sine. So 2 over 2 I times sine k delta x over 2. And this is minus I omega p naught. And then the same thing for the u equation, because it's basically the same equation with u's and p's swapped around. And so the dispersion relation now looks like this. So we have this factor of 2 in here, of course this factor of 4, and then here we have because we basically substitute the p equation into this, and now here this factor of 2 comes down here, and so this dispersion relation looks similar, but there's some crucial differences. So k max is still the same. So k max is just pi over delta x. So k max, and so this, instead of being pi, is now pi over 2. And so if you plot the dispersion relation, and we go and k, so again the analytic omega is equal to k. K max is here, and we find that's pi over 2 here, so this is when sine is 1. And so the dispersion relation essentially looks like half, turns out something like this. So you end up with a velocity which starts rolling over but doesn't actually go down to 0. And so you end up with basically omega by dk is always positive, so always in the physical correct direction. And you don't end up with this zigzag mode with 0 frequency that you have in the cell-centered case. So this is quite a nice property for waves, that you can capture much better the dispersion relation and avoid some of the unphysical waves at high k on the grid scale. So it does have some disadvantages as well in terms of conservation properties and complexity. These are some of the trade-offs you have to make when you're choosing a numerical method.